Have you ever wondered how TVs evolved from fat and bulky boxes to slim and flat monitors with the revolutionary LED displays that they are built with? Most of the known and big-time brands now use the so-called QLEDs. This type of displays makes use of quantum dots, which are nanoparticles that range between 2 to 10 nanometers in diameter. Now the question is, how do we make nano-sized particles like quantum dots? In this video, we reveal the major mechanisms involved in the synthesis of nanoparticles. The synthesis of nanoparticles is generally divided into two mechanisms: kinetic approach and thermodynamic approach. The kinetic approach can be done by introducing a limiting amount of precursor for growth or limiting the space for the process like in micelle synthesis. On the other hand, the thermodynamic approach, which is the focus of this video, can be accomplished through these sub-processes: supersaturation, nucleation, and growth. In order to undergo nucleation, the growth species must be saturated. This is the state of the solution where adding more solute to the solvent will not increase the concentration of the system. Supersaturating can be attained through a reduction in temperature or in situ chemical reaction. Once supersaturation is achieved, nucleation commences. For the succeeding discussion, solution synthesis will be looked upon to tackle the fundamentals of the process, particularly concerning the formation of nanoparticles. This type of synthesis is defined by having a system with a high solute concentration, which exceeds the equilibrium solubility of the chemical to form a new phase. A supersaturated solution has a high free energy. The formation of a solid phase reduces the free energy, at the same time conserves the overall equilibrium concentration of the system. The reduction of this free energy is the driving force of the process. This indicated energy is also the free energy difference between the solid phase and the liquid phase, or is also referred to as the free volume energy, denoted by delta GV. The free volume energy is dependent on the solute concentration C, temperature T, and the supersaturation sigma as shown in the equation. Herein, we can see that the absence of supersaturation consequently leads to no nucleation. Additionally, spontaneous nucleation occurs for systems with larger solute concentrations compared to the equilibrium concentration C0 because of the negative free energy value. Assuming that the nuclei formed is spherically shaped, the volume free energy can be expressed in We can see here the trend of the overall free energy as a function of the atomic radius r. The increase in the atomic radius would lead to a more negative free energy change, a more favored formation of the solid phase, specifically third-folds of the radius value. However, the energy reduction which is caused by this factor is counterbalanced by the formation of an interface between the solid and liquid phases. Hence, the formation of nuclei in the system is accompanied by an increase in the change surface energy, delta mu s, described through the following equation. In the interface exists gamma, the surface free energy. The contribution of the surface energy term is coupled with the surface area of the nucleus, 4 pi r squared. Reflected in the equation, the increase in surface energy is factored by twice the radius value. The free energy versus atomic radius graph would then result to this. Overall, the resultant of these factors is the total chemical potential change for nucleus formation, shown in dashes. This shows the behavior of the atoms in the supersaturated solution. Initially, atoms in the liquid phase gather together to form the solid phase, thus having a positive free energy change from a higher contribution of the increase in surface energy than from the free volume energy factor. A maximum is observed in the graph wherein we introduce some critical terms R star and delta G star. The decrease in the surface energy will then be observed after attaining this maximum value, for the process is thereafter accompanied by the growth of the nucleus. In such case, nuclei with radii larger than R star are stable, whereas those which are smaller dissolves back to the solution, effectively decreasing the overall free energy. The corresponding change in free energy to achieve R star is the value delta G star. Physically, we can also treat delta G star as the energy barrier needed to be surpassed in order to form a nucleus. These values can be obtained by getting the slope of the graph at the maximum point, which is d delta G over dr equals 0. The resulting values are, from this equation, it is shown that the free volume energy change is a function of temperature, which consequently means that R star and delta G star are also functions of temperature. Therefore, as shown in the graph, the increase in temperature results in the decrease of these critical values. As a result, a process temperature that is lower than the equilibrium solidification temperature readily produces nucleating sites. After this temperature is attained, a considerable nucleation rate is achieved. The phenomenon associated to this process is called supercooling. Hence, at supercooling, smaller particle sizes are achieved, whereas for higher temperatures, larger particles are obtained. The foregoing nucleation mechanism revolved on a perfect system consisting of the solution components only. However, in some systems, the activation energy for creating nuclei delta G star is reduced brought by the presence of pre-existing surfaces, which effectively decrease the surface energy contribution. This mechanism is termed heterogeneous nucleation. The critical values are then equated to. It is important to note here that the critical radius is similar for both homogeneous and heterogeneous cases, and only the energy barrier decrease in value. Differentiating these values is the factor S theta, which is deterministic of the shape of the nucleus, wherein its values lie between 0 and 1. Hence, for this type of nucleation, the energy barrier for the heterogeneous process is factored with S theta with that of the homogeneous process. The size distribution of nanoparticles is dependent on the subsequent growth process of the nuclei. The growth process of the nuclei involves multi-steps, and the major steps are generation of growth species, diffusion of the growth species from bulk to the growth surface, adsorption of the growth species onto the growth surface, and surface growth through irreversible incorporation of growth species onto the solid surface. These steps can be further grouped into two processes. Supplying the growth species to the growth surface is termed as diffusion, which includes the generation, diffusion, and adsorption of growth species onto the growth surface, whereas incorporation of growth species adsorbed on the growth surface into solid structure is denoted as growth. A diffusion limited growth would result in a different size distribution of nanoparticles as compared with that by growth limited processes. Let us first talk about diffusion controlled growth. When the concentration of growth species reduces below the minimum concentration for nucleation, nucleation stops, whereas the growth continues. If the growth process is controlled by the diffusion of growth species from the bulk solution to the particle surface, the growth rate is given by, where R is the radius of spherical nucleus, D is the diffusion coefficient of the growth species, C is the bulk concentration, Cs is the concentration on the surface of solid particles, and Vm is the molar volume of the nuclei as illustrated in figure 3.6. By solving this differential equation and assuming the initial size of nucleus R0 prime and the change of bulk concentration negligible, we have for two particles with initial radius difference, the radius difference decreases as time increases or particles grow bigger, according to, combining with equation 3, we have both equations 4 and 5 indicate that the radius difference decreases with increase of nuclear radius and prolonged growth time. The diffusion-controlled growth promotes the formation of uniformly sized particles. Now let's talk about growth controlled by surface process. When the diffusion of growth species from the bulk to the growth surface is sufficiently rapid, that is, the concentration on the surface is the same as that in the bulk, as illustrated by a dashed line also in the figure, the growth rate is controlled by the surface process. There are two mechanisms for the surface processes: mononuclear growth and polynuclear growth. For the mononuclear growth, the growth proceeds layer by layer. The growth species are incorporated into one layer and proceeds to another layer only after the growth of the previous layer is complete. There is sufficient time for the growth species to diffuse on the surface. The growth rate is thus proportional to the surface area, where Km is a proportionality constant dependent on the concentration of growth species. The growth rate is given by solving the equation. The radius difference increases with an increasing radius of the nuclei. Substituting equation 7 into 8 yields. This boundary condition is derived from equation 7, and it means that the radius is not infinitely large, that is, r is less than m. Equation 9 shows that the radius difference increases with a prolonged growth time. Obviously, this growth mechanism does not favor the synthesis of monosized particles. During polynuclear growth, which occurs when the surface concentration is very high, surface process is so fast that second layer growth proceeds before the first layer growth is complete. The growth rate of particles is independent of particle size or time. That is, the growth rate is constant, where Kp is a constant only dependent on temperature. Hence, the particles grow linearly with time.